100 years ago in North Carolina, Wilbur and Orville Wright got their powered aircraft and the entire aviation industry off the ground with two great breakthroughs: powered flight and controlled flight.
Wilbur and Orville discovered how to do it by observing the way birds fly. But they only copied the bird's control system. Unlike many other pioneers of flight, they realized they wouldn't get airborne by flapping. So, is there a scientific reason why no one has ever managed to fly by flapping wings like a bird? Or would it be possible, with modern materials, to make a passenger-carrying, flapping flying machine? Welcome to Science Shack.
We've brought the shack to Bristol Airport to try and answer the question, could you fly like a bird? And by the end of the programme, I want to be flying all around this hangar using flapping wings, just like this little chap.
A tricky challenge for the Science Shack team of engineers and scientists: Alom, Janet, Sim and Jem.
That's cool.
So, OK, can we do it? Can you get me flying like that? And if so, can I have silver wings, please?
The silver wings we could manage a lot easier than getting you flying like that.
Now, I am a bit heavier than this chap. Janet?
Oh, we're going to need a fairly massive wingspan, aren't we?
You know you want to fly with flapping wings? Well, the bigger the bird gets, like really big, they don't hardly flap at all. How much flapping do you have to do to justify flying with flapping wings?
The occasional flap.
Just
I'll
the
be happy
occasional
with
flap.
the occasional flap, yes.
Right.
Well, if you'd like to get on and start making me some wings, then we at least have a chance.
I'd like to point out, at this point, I'm sceptical.
You think it's impossible?
It's going to need some sort of cunning.
It's never been done before, Adam. No human has flown with flapping wings.
It does not sound promising, but let's get started.
OK, thanks, Adam.
It's kind of snappy.
Cool.
If the team pull this one off, we could change aviation more than the Wright brothers did.
All the early pioneers of flying studied birds, and many of them tried to make flapping wing machines. The proper name is ornithopters. Even Leonardo da Vinci designed one.
Leonardo made detailed sketches of his single pilot design, although he never quite got round to building the real thing. But if birds can do it, surely scaling it up to people size can't be too hard.
Why is it so difficult to achieve mechanically what birds do naturally? For anything to fly, you need two forces. You need lift to counteract the weight, and you need thrust to move it forward. So, suppose I want this bit of wood to fly. First of all, I need something to hold it up, and then I need something to push it forward. Well, I've got some lift up here. And if I attach that to my piece of wood, then that ought to sort out the problem of weight. Let's just see. Yes, that's going nicely upwards now, which is, I'd rather it was going upwards than downwards. Now, second, I want a force to move it forward, thrust. So I'll attach that rubber band there. Then I'm going to wind it up. There we are. I reckon that should be enough power. Now, 1, 2, 3, go. Yes! Look, it's flying. So all you need is lift and thrust, and you've got flight. Although I have to admit, I lack a certain amount of control.
Birds somehow get lift, thrust and control just by flapping their wings and adjusting their tail feathers. It's hard to understand exactly how they do it, so we've flown in an expert to help the team. Paolo Viscardi is a biologist from Leeds University. He spends his days persuading budgies to fly in a wind tunnel so that he can film them and study them at leisure.
Okay, and when you're flapping...
As an experiment, the team have made 2 simple plywood shapes just to see if I can do anything with them. And Paolo's first job is to teach me how to flap like a bird taking off. Maximum resistance as I push down, a nice streamlined shape as I lift up. And Sim has built me a kind of seesaw.
Am I balanced?
Nearly.
The idea is to counterbalance most of my weight.
Yeah, he's about okay
let's see
there.
what lift you can generate.
All right.
Oh, yes.
Going?
You're going up.
It's good.
Excellent.
Brilliant.
It works. It works. Gosh. But clearly you can displace the air downwards, can't you? It's just like rowing, essentially.
Exactly the same, just different fluid.
Up. Get up. Up.
No, you're lifting. We've got half of the flight.
Right, now we'll try and
Bravo.
I'm impressed.
That was really good.
Good. Well, that's solved. We've got power flight.
Yeah.
That's it. The end.
I did manage to go up slightly, but with virtually all my weight being taken by the seesaw and by throwing a huge amount of air downwards. It just shows how hard it is to do what birds do. Doves can lift their entire weight off the ground using their wings this way. But staying up using this type of flapping would be exhausting, especially for bigger birds. So, once birds like albatross are in the air, they use their wings in a quite different way, flapping occasionally, but spending a lot of the time gliding. They can do it because the wing has a special shape called an aerofoil.
6, yeah.
The team reckon that I'll do better with shaped wings too.
7.
Pull it out, pull it out, pull it out. I'm on 1.
Yeah, me too.
But to have any chance of flapping them, they'll need to be very light.
Pull it, keep it really
So they're using a hot wire cutter to shape a lump of polystyrene, and it's a delicate operation.
Yep.
4 1/4.
Yeah. No.
Oh!
That was the end of the wire.
What? As I suspected. It is.
You can't rush hot wire cutting.
Slow it down so it really like 4 1/4. That's looking low. Oh,
that's not bad at all, is
there. This is the killer ingredient.
The foil will smooth the surface of the wing and should smooth the airflow.
Coating on it, then we'll get a fairly smooth lifting surface anyway.
So why do curved wings give better lift? I asked Holger Babinski from Cambridge University to explain with the aid of his portable wind tunnel.
Well, what you can see is that the flow actually tries to follow that curved upper surface.
Yes.
The lower surface is reasonably straight, but again you see there is a little bit of curvature.
Being pushed downwards. Yes.
And this tendency of flow to follow along curved surfaces is something that we know from daily life. And if you would hold that bottle of water for me.
Okay.
And yeah,
Okay.
pour that into the bucket.
Okay.
Hang on, I hold the bucket.
Okay.
If
This
we
is very technical, isn't
pour
it?
this straight down, yes.
Straight down, like that.
If I now put a curved surface in, you see how it follows around that curved surface.
So that's the Coanda effect.
That's called the Coanda effect.
That's why my
exactly.
teapot dribbles.
That's exactly right.
Right,
yes.
okay. And you say that's what's happening to the smoke?
It's effectively what's happening is something very similar. It's this tendency of the flow to follow along the curved surface.
Right.
If you look at the flow direction before the wing, it's going sort of upwards.
Yes.
And behind it's going downwards.
Right.
And it's that change of flow direction, that curvature, that generates lift.
Now, your aerofoil and indeed aircraft have flat underneath to the wings, don't they?
Relatively flat, yeah.
But some birds have got sort of concave underneath. Herons. They look like spoons, don't they, when they fly?
That's right, and in fact that's very similar to what sails on boats do. You're actually changing the flow direction not just with the upper surface but also with the lower surface. So they actually can generate
They're more
lift.
efficient.
Exactly right,
More
yeah.
efficient. So why don't they build planes like that?
Well, because the wing needs to have some structural stiffness, and if you had a thin wing like that, it would...
You go splat.
That's right,
Yes,
yeah.
I'd rather not do that.
So, some birds manage to stay in the air while hardly flapping at all. They get lift when air flows over the curved surfaces of their wings.
Watch out, Sim, you'll get your head knocked off.
And the team are hoping that their new aerofoil wings will do the same for me.
We've got to move this, I think.
You going up?
Am I?
Yeah,
Oh,
that was
yes, I've
going
gone
up.
up about a foot. I can't tell the difference with different angles.
Try angling it down, see if you can start
Angle
going
it down.
See if you can...
See if I can ground it.
I think it needs to go.
Doesn't make any difference. Oh yeah, hey, it feels a significant difference when I turn from down to up. I can feel it lifting my hand. I think there's not enough force.
This is promising. I'm getting real lift from the wing without flapping. But aerofoil wings only work when you're already moving. That's why planes have engines to thrust them down the runway. So how do birds get going in the first place?
By flapping their wings, birds generate thrust. And I'll show you that. This is a tin bird, and rather than having him flying around, we've put him on this little trolley here. So
switch him that way.
Switch him that way. And off he goes. There you go.
He didn't fly much, not enough lift, but he certainly had thrust. Yes,
he certainly had thrust, so he pushed himself forward.
Right.
That's rather surprising. It means that birds like ducks don't flap to generate lift, but rather to thrust themselves forwards. Then, air flowing across their wings keeps them up.
So if I can get this trolley to move by me flapping my wings...
The team reckon that once I'm aloft, I should be able to get thrust by flapping my polystyrene wings in a special way.
How are you going to flap?
I was going to flap as if I was lifting myself.
OK, well,
so like that.
That's basically how a bird's going to be flapping when it's taking
like that, yeah.
OK, give that a go, see what you can
Janet,
do.
Okay.
if you all sort of clear my flapping zone.
It's working.
It's working.
That's a bit disappointing. There's some thrust, but Jem's not exactly breaking the sound barrier.
Oh, watch out for the wings.
You might not take off.
I'm not going to get lift from the wings at that speed.
I thought it might be interesting to reverse engineer a bird to see what it's got inside that allows it to fly, and then perhaps we could put a bit of bird engineering into our design. Now, you guys might prefer to look the other way. Now, here I've got a dead chicken and a dead duck, and I want to investigate their various sorts of muscle. Now, as you know, birds have red meat and white meat. So let's have a look at this chicken breast. Make a nice carve there somewhere. Down to the thing, open it up, and look at that. Lovely white meat, absolutely no doubt about that. And the reason is, white meat is the sort they need for instant bursts of activity if they want to fly away from a fox or something. And if this chicken is anything like my chickens, the only bit of flying it does is fluttering up to the coop in the evening. All the rest of the day, it wanders around looking for food, which is why its legs have red meat, because that's the sort of muscle that's used for endurance, for long sustained effort. Let's have a look at the duck. Into the breast again. There, look, it's all red meat. And that is because ducks do a massive amount of flying. They fly huge distances. They really need that sustained effort. They need the endurance muscle. The red, incidentally, comes from a chemical called myoglobin. But both birds are packed with muscle.
This rather cheap model shows what I would look like if I had scaled up bird chest muscles. Great for flying, but hard to blend in down the pub.
You're not going to get me.
So the team will have to move away from muscle power.
No.
There are chaps out there, I don't know if you've noticed, but there are aeroplanes flying around and they use engines.
Absolutely.
Do you
They
think
also
we could...
cleverly use fixed wings.
Well, I know, yeah. But don't let's worry about that. Do you think we could use an engine?
We can try, Adam. Again, I wouldn't stake your mortgage on it, but we'll try.
There'll be more power in an engine than in
There'll
my
be a lot more.
shoulders,
There'll be
won't
more
there?
weight.
That's probably
There'll be
true.
more power for its weight as well in an engine.
Good.
So we'll give it a go.
OK, engines, try engines.
All right,
Thanks a lot.
engines it is.
Everything that flies has to deal with the dreaded power-to-weight ratio. The largest plane and the smallest bird need enough power to generate enough lift to overcome their weight. A dove taking off uses about 200 watts per kilogram, so it's burning as much energy as an electric drill at full power. Scaling that up, I'd need to generate over 20,000 watts to get airborne. Even a super fit athlete can put out only a tiny fraction of that. So I'm never going to get airborne under my own power, even if I use something like a bicycle to gear it up. And birds have got some other evolutionary tricks up their feathery sleeves. Have a look at this pigeon. Well, it doesn't look terribly well, does it? I think, in fact, it's an X-pigeon. It's got a paper-thin skull. And then a whole lot of its bones have been fused together, partly to save weight and partly for strength. All its vertebrae here, this here, which looks like two bones, but actually has been fused together to make one, that corresponds to our wrist. We've got lots of bones, only one there. And then the fingers, you see, all fused together. In fact, the only place it's got big bones are its chest here, and then of course, the upper arm or wing, where it needs great big muscles attached to those bones. And not only that, a whole lot of the bones are hollow. This is the leg bone of a chicken, and just look, it's completely hollow inside to save weight. Brilliant, isn't it? A really engineered for flying machine. This is a beautifully engineered for flying machine too. Lionel Lawley and Nigel Druce are Science Shack viewers whose hobby is making rubber band-powered ornithopters.
Lionel, you think this is going to fly, yes?
I hope so, yes.
For how long?
Probably about 20 seconds. There's not too many turns on the rubber. So.
OK, well, why don't you launch that sort of in that direction, if you would? Oh, fantastic.
These delicate machines are made from tissue paper and balsa wood.
A lovely left-hand circle. Going up and up.
They're as light as possible and need only a tiny amount of lift to keep them aloft.
Is it trained to come back to you?
Not necessarily, no.
And when it lands, does it just plummet?
It glides to a certain extent.
Well, you can't win them all. That's a great flight. Now, Nigel, how about yours? It looks more elaborate, this machine.
Well, yes, it is. It is rather sophisticated.
Still powered by a rubber band. Yes. Right. Now, you've got cranks on the front, so both wings go
Both wings go up at the same time.
Oh, yeah.
And down at the same time.
OK. How long did it fly for?
Well, this one has actually flown for over a minute.
A minute?
Yes.
I find that hard to believe. If you would launch it in that direction... It goes on and on. Bits of swooping. What do you think, Paolo?
Absolutely spectacular, they really are. And that's beautiful. That flies very much like, say, a seabird or maybe something like a goose. So you've got this stiff part of the wings at the base.
One by the shoulder, yeah.
And then you're getting all the thrust generated from the flapping at the tips.
So it's actually separating the lift and the thrust.
Yeah, and that way, by doing that, you can generate more lift and you can fly for longer. So you use less power by using aerodynamic forces.
It's very clever.
It's absolutely amazing.
If you'd like to have a go at making a rubber band-powered ornithopter, there's details and plans on the Science Shack website.
Oh, hang on, isn't the front going to tip up?
Well, it should be all right.
The Science Shack team have turned to an old mini-engine to power their full-size ornithopter. And instead of tissue paper wings, they're going to use windsurfing sails.
If we pop that in there.
The plan is to strip the Mini to the bare essentials to save weight, and then mount it on a lightweight trolley so it can roll.
Can I connect this up now?
Yeah, connect that now. Does that turn?
They'll use one of the Mini's drive wheels to move the wings.
So this is our flapping wheel.
But have the team got any chance of getting me airborne, even with an engine supplying the power? Well, the largest creature that ever flew lived 25 million years ago and was called Hart-Davis magnificans. And the good news is, its body was the same size and weight as mine. Of course, it had an 8-metre wingspan and huge muscles, but at least there's a glimmer of hope.
Right, so that'll do for a minute, and let's...
25 million years of evolution later, and the Science Shack team are getting quite excited.
It should be... flying like a bird! Can you feel the air?
Yeah, it's blowing in my face.
Excellent.
Ah, fantastic. It flies.
It does.
It flies.
The largest engine-powered ornithopters to fly so far are radio-controlled models like this one, built by Science Shack viewer Dave Polson.
It looks like a sick bird, doesn't it?
It does. It's
yes.
It's very windy up there, but it is being controlled now. As you can see, it's hovering well in the wind, into wind.
It doesn't look easy, though, to control.
They're not easy at all, no.
So you wouldn't let me have a go?
I'm afraid not, no. the pilot at the moment has been flying for 40 years plus.
How big do they come?
That is the largest sort of commercially successfully available one today, at 59-inch wingspan.
59 inches?
59 inches.
Okay.
Yeah.
A lot of lift it's got up there. And
it has, yeah.
How do you land?
About like this, I think.
Oh, that was very delicate.
Exactly like
I'm really
that.
impressed. That was fantastic. It looks as if you just switched off.
That was one of the better landings, I must say.
It's not always like that.
No, it's not.
So it's really hard to control in the landing, is it?
Very much so, because you're losing power, so you're losing your airspeed because your wings are flapping slower, so you have got to try and glide it in.
And basically you're liable to go splat.
Yes.
OK, now just show me how the controls work. How do you flap, first of all?
OK, there's obviously an electric motor that's geared, and then from the transmitter we give some control, which flaps the wings.
Ah, now, it's interesting that the trailing edge obviously comes down later than the leading edge.
It does.
So it's a sort of flap, almost like flippers on the back of a swimmer.
It's actually taking the same shape as like the fingers on feathers on a real bird.
Right.
When you actually see it, it actually takes different shapes,
Yes.
as you notice, yeah.
Yeah. Now, what about left and right?
On the rear, you have the tail, which from the transmitter you can direct for direction.
The whole thing just swivels over.
So that is for your left and right direction.
Right. And up and down?
Up and down. Again, on the transmitter, you have another control.
Just goes up and down?
And it goes up and down.
Simple as that. So in principle, it's easy.
In principle, it's very easy, yes.
Real birds can control every feather individually. Another reason why it's so hard to reproduce flapping flight mechanically.
Whoa.
Oh dear.
Let's hope the team have better luck. They aren't expecting to get airborne on this test. They just want to see if the windsurf sails will generate enough thrust to move the flapper down the taxiway.
Get chunks away!
Well, let's get rid of these.
Can I go? Tell me when to start flapping.
They've connected a crank to one of the drive wheels of the Mini so that it will push the wings up and down as the wheel turns.
I'm going to put something in here.
Shall I just lean in and
Would it
press
help
it?
if they started on the upstroke? Shall we give Gemini hold on?
No, it won't matter.
If they can get any thrust at all, they should be able to get extra lift by adding another set of fixed wings. Then maybe they'll be able to get the world's first person-carrying ornithopter off the ground.
Give it a bit more gas.
I think it's that you win. Oh my God. It's just snapped that. That's all power.
It's such a whippy action. That was
I don't think that works, gents.
brilliant.
No windsurfing this weekend, then.
I suppose it was flying in the face of experience to hope that a fly-by-night machine knocked together in a few hours would really take off. Even professionally designed and built ornithopters have never succeeded in carrying a person into the sky. The nearest to success is this Canadian machine that only managed to hop, skip and jump down the runway. So it's not looking optimistic for the Science Shack team.
I do think we've got a problem because, you know, with huge effort, I've managed to get 1 foot off the ground. We are not going to fly, are we? To be honest, we're not going to get off the ground.
Yes, we are.
We are.
Because we do actually have a plan.
You have a plan?
Yeah, and it is more cunning than a flying fox.
Huh. Huh.
Because you may be heavy, but there's no reason for you not to be buoyant.
Jem's plan is indeed cunning, and if you want to find out whether it gets me flying like a bird, keep watching. I'm starting to wonder why birds fly like birds. Flapping is an inefficient way to get airborne, and in flight it seems pretty unstable. So why do birds do it?
It's not just about generating the power to fly, it's also about control. Because if you're deforming your flight surface, your wing, then you've got manoeuvrability inherent in that system. It means that you can change the amount of lift that you want to generate by altering how much you've got one wing out, for example. Or if you're going to a glide, you can raise one wing more, so you can actually change how you're moving in the air. That's important. You can also change the amount of lift that you're generating very, very, very finely when you're flapping. And as a result, you can be manoeuvrable. You can be a hunting animal, like, say, a peregrine falcon, which can go into steep dives. You couldn't do that if you didn't have a flapping wing. They fold their wings against their body as they dive.
Right.
And that's what gives them the streamlining. It
so
makes
they really have got
incredible control.
Right. Presumably, you can never get that sort of manoeuvrability with an aircraft.
It's very difficult because you've got a fixed wing, so you can't deform it in the right kind of way. And manoeuvrability, I mean, it's related to instability. So if we try to do the same thing, you get planes like the Eurofighter, which have got 3 supercomputers on board, so that they can be unstable and therefore be manoeuvrable.
You mean it's impossible to fly without...
You couldn't fly it without the computers. You'd just fall out the sky and crash.
So, being unstable is good. It means birds are much more manoeuvrable. They can hunt and evade predators. And that is why flapping evolved. I'm hoping I won't need to evade predators as I flap around the hangar, if Jem's cunning plan works. The team have accepted that I haven't got enough power to lift my own weight, but inspired by the light hollow bones of birds, they've been thinking laterally. There's no way to increase my power output enough, so why not reduce the weight? And they're going to do that by attaching me to a giant helium-filled balloon. Now, they tell me I'm now about to fly like a bird. Paolo, can you give me some advice for takeoff?
Yeah, well, all birds, when they take off, if they're taking off from the ground, will always jump. So you need to have that jump, otherwise you can't move the wings.
Right, so jump and then flap, yes?
Jump and then flap.
OK, well,
now,
here goes.
There's no rush. There's no rush. Remember,
really?
You're better to have a motion which works than to have one which is like all over
Slow.
the place.
1, 2, 3, jump! Oh!
That's good.
Oh, I've got lift.
Excellent.
I've got lift.
Hey.
I'm flying. Now, can I go forward? Can I go forward? The balloon isn't taking all my weight. I'm still slightly heavy. If I stop flapping, I sink back to the ground.
Forward.
Keep going.
Well, there's definitely air going backwards anyway.
You're certainly moving.
Yes.
Adam.
Keep going, keep going.
I'm actually flying like a bird.
I can certainly feel the air you're pushing back.
I'm achieving lift and thrust by flapping. Although I'd accept my control leaves a bit to be desired. That's why the guys are holding onto the loose tethers, just in case.
That's very good.
No, that's excellent.
Keep going. It's good motion.
Well, we're headed south. Maybe France for a drink before dinner. And just like a bird, I've evolved to be very light. OK, with a helium balloon rather than hollow bones.
I can feel the breeze down here.
Well, so the team have done it. Jem, what are you doing?
This is flow visualization. This is the proof that you're thrusting air downwards.
Excellent.
Look as you go over it, Adam. You're just totally clearing it.
Fantastic. And if you notice, it's all going kind of away from you, that way and that way. It's not really going in front of you very much.
Even back here, you're still
So it shows
moving
that you're flapping
polystyrene. That's a lot of air you're throwing down, Adam.
Well, they said they'd make me fly like a bird, and here I am flying, well, a bit like a bird. Thank you, gang. I'm headed south for the winter. See you next time. For a free Open University magazine that features Science Shack home experiments, call 0870 900 9581 or visit www.open2.net. Now, does anyone know how to land this thing?